Good afternoon, my dear students. My name is Chiravachradej. Today we meet again for the lecture for the statics course, aka engineering mechanics. Today we will discuss further on the cable. This time we will expand the idea. Last time we just having to see the mechanics of the cable with a point load. This time we will look at the cable that's subjected to distributed load. Okay. So let's see what we have to go through. Okay. We will talk about the application of the cable taking the distributed load first. Why do we have to study them? What is the civil engineering application for it? Okay. Then we'll talk about the formulation, how we generate the equation and how we solve, how we prove for the equations. And then we'll see the example on how we actually analyze the forces inside the cable and all the features that are associated with the cable itself. Okay. Well, it's usually these days, I think we discussed this before already. Today, when we have a last span, they found a technique that reduce the way, rather than using only the beam to take all the forces. They can use trusses, of course, or any form of solid structure. They found a technique that actually help reducing the cost and the weight of the structure itself while still maintain the safety and the public confidence on using it. In this one, they use the cable stay bridges. Okay, this is one probably in Britain, I think. I'm not too sure though. Okay, then this is America. I think it's the Golden Gate Bridge and another bridge. Notice that the span is very long, whereas the size of the structure, the thickness of structure, is not as thick as without the cable. Okay, with the cable, it helps transfer the load directly to the columns and to the ground, rather than everything has to go through the beam. Okay, so this is the way the schematic go. We have the beam, and then we have the two anchors on the both sides, and of course some columns in the middle. Oh, well, not really in the middle, between the span. Usually this is really long span bridges. Okay, the cable, we have the suspension under the tension, of course, and the main cable also under the tension. Okay, then let's go continue. Okay, now the way we formulate it. Okay, this is the idea. The two support, although draw as if it is having vertical wall, it doesn't actually mean that. It just symbolizes the pin support, meaning at that point, well, we know that cable only take tension, and cable doesn't resist any bending moment. Therefore, the way of constraint is already not, it allows to rotate at the touch support, whereas it doesn't move either left or right or up down. The cable should stay there at the support. It does actually means we have to hang it on the wall. It could be a column upwards, but the pin type still there. The pin support type still there. Okay. Now the main cable is the one that we look at in the middle span, and then of course we have the suspension, or the vertical cables, right? Now that part, then the slab, or maybe the beam, depending on the system of looking, but usually it's the beam, then hang onto the cable. Okay. Now the load, of course, come from the self weight of the build. That load, the build, can come from the beam, from the slab, from the pavement, and of course from the traffic on the bridge. Right? The traffic go into the pavement, into the road. Then the weight of the road, the weight of traffic transfer to the beam. Okay, and rather than go through the beam, rather than all of them going through the beam to the column, then most of it will actually go to the cable suspender and then hang up to the main cable. Right? So this schematic, that W at this moment in time, we are not discussing it as if it is any function yet. But as far as I'm concerned, x is the distance in the horizontal measurement. That means that although at the moment we don't know the exact magnitude, we assume that, well, which in fact in reality we can describe this W with the function of distance, meaning we can actually, once we derive that function, then of course we know exactly where what is the magnitude of the W at any single point. So Now when we look at this, since we are talking about the coordinate x, y, okay, rather than starting off without any origin, then we start off setting up the origin at the lowest point. I have to emphasize on this wording because it is of very importance. The origin of this coordination x, y will start at the lowest point of the main cable. The advantage, or in fact the necessity, will be apparent later when we actually prove the formulation. Okay, but at this point in time, just mark that the origin is not at the support on the left or the support on the right. It's not anywhere but the lowest point in the main cable. Right. So in that case, I mark the red spot there, meaning when we set x, y, we will set it as such there, x and then y. Okay. Of course, this one here is more like the structure that resists weight. So the weight tend to be vertical, and of course the structure tend to be, in this case, if you look at it, horizontal, right? So usually this y, x and y set horizontal and vertical. So now there we go. Well, now because the load is changing, of course the tension probably changing. So rather than look at the whole thing as a whole, then as usual, when things keep changing, we look at a small specific place first as a representative, not as the fixed value, but as representative. In this case, we look at a small cable, the more part of cable. Oh, by the way, this one here, although it goes through the suspender, it's actually assumed that it distributed equally, as if the distributed load is attached to the main cable itself. Okay, that is theory. It's not exactly true, but usually there will be some rule saying how far the suspender can be to allow that assumption to be true. Okay, but that is again in a higher course. Now, once we choose a part of it, then as I said, we assume that the load W in the bottom, the blue, just can be subject directly to that part of the cable itself. So basically transfer into that picture there. Okay. Notice that the small side of the cable, okay, it is not assumed straight line, because in fact, if you assume straight line, then it means that it's the same tension throughout, which is not quite true in this case. So let's see what happens. At the edge there, bottom left of the cable, it is not horizontal, it's in angle. Okay, that's small dx. W, however, is if the x is assumed to be small enough, then of course it's assumed to be kind of like straight line function. Okay, so I just draw it straight. Now, of course, this is a cable. This is free body diagram. This picture on the left hand side is the free body diagram of that small part of the cable we call dx. Okay, so there we go. Then of course, if we cut the cable at the cut point, it touched the other, which means the other side of the cable. Okay, and the condition of the cable is that it only takes axial force. In fact, it only takes tension, which is only one sign of axial force. But anyway, it's tension, right? So we know we can draw it. Okay. Now, because this is not a straight line, usually the tension is, of course, will be at the point with different angle. In this case, we'll draw it with the tangent line. So that is the tangent line on the 2 points. So the two forces will look as such. Okay. Now on the left hand side, okay, which is starting point, usually is x and then move this way dx, right? So the starting point, let's say it has a tension that we call T. Okay. Now if we move along the cable in that small dx, we are not so sure it's going to be the same. In fact, we'll be proving that it's not the same in the end. But anyway, just to allow it could be changed, rather than call it T1 and T2, we'll call it that one T, though that one will be T plus any change that might happen. Because it is small distance dx, the change will be small as well, so it becomes T plus dt. Okay? So T is the same T, the same value at the T on the left hand side, and dt represent the change inside that happen when you move across distance. Now, of course, if you look at the tangent line, you should notice that we in fact have different angles, right? So if the beginning point, the angle between the horizontal line and the tangent line is theta, as I indicate there, then Next, when we come to the end, it's no longer a theta. This one is clear because the slope keeps changing from one place to another, correct? Therefore, on that path there, it cannot be theta. Similar to the idea of the tangent of the tension, then we use the same idea. Rather than theta 1 and theta 2, we use theta and then theta plus any change that might happen. So theta plus d theta. Okay. So now in that free body diagram, we have all the forces acting on the body. We know all the angle. Well, or at least we have a symbol for all the angles that involve with the forces. So we're going to carry on and move on to start to prove the relationship of T with the W, of course. Okay, so I take off the picture of the geometry, leave the free body diagram, then we're going to use some equilibrium here. Okay, the first one we look at this in this one, we look at sigma fx, the summation of all of forces on the x-axis. Okay, of course there's only two of them. The tension on the left hand side, T. The tension on the right hand side, T plus dt. W is downwards, right? Not involved. So when we put it, of course we take component, then we have T going to the left, negative, sorry, going to the right, positive. So we have minus T take into theta, and then we have d plus dt take the angle of theta plus d theta. Okay. Now, before we can solve forward, we look at it and, well, we probably have to expand the term, or well, we actually have the expression of cosine A plus B. Okay, this is in, I think it's geometric calculus or something. Okay, but anyway, so we know this equation exists. Okay, so rather than leaving it as two angle plus inside, we spread them out. Okay, so we have in this picture there. Okay, now before we expand it, okay, now this theta is quite small. Okay, and this theta here I have to state right now, because for the rule, this rule to be true, the theta must be in radian unit. So if this theta is really small, approaching 0, which it is, okay, and now from this point on, we should know that the unit will be radian. Okay, then cosine d theta is approaching 1, and sine d theta is approaching d theta. Okay, having that in mind, then we can simplify our equation into this form. Basically, substitute cosine d theta equal to 1 into it, and sine d theta as d theta into it. And then notice the second term, in fact we have two terms multiplied by two terms, so we're going to expand it, okay, in all 5 terms. Now we start to notice similarity. Okay, some of them are the same term, but and one is plus, one is minus, so we eliminate them. Okay, and then we end up this way. Notice the last term. The first two terms, t cosine minus t cosine plus t cosine, disappear. Okay, the last term of that equation is minus dt sine theta d theta. dt is really small, d theta is really small. Two very small numbers times each other, it is not 0, but it is negligible. So we ignore it, and we have only two terms left to the next equation. Now, well, I run out of the space, so I'm going to move the equation upwards to the top there, and we're going to continue with that. To explain this, I rather go to the end and then explain backwards. Okay. We should notice this different. Okay. This in the top equation, it is dt times cosine theta. Okay, meaning you have a small t times the full cosine theta. Okay, this one here you differentiate t cosine theta, meaning t times cosine theta, and then you differentiate it. That one is differentiate t and then times cosine theta, different one. Okay. Now, if we set up equation as that, okay, notice that it's differentiation of u times v, so meaning we can expand into that term. Differentiation of u times v, and then differentiation of and then u times differentiation of v, right? That's the normal expansion for when you have two terms times each other and you have to differentiate it. Okay, this is calculus. Then in that case, the first term will remain, but the last term, the d cosine theta, we can expand into the differentiation of the function inside variable inside the function and differentiation of function itself. Okay, the chain law, I think it's called the chain law, chain rule. Okay, basically we can change it in that term. Okay, from t times d cosine theta. D cosine theta is in fact minus sine theta d theta, and therefore we substitute into that way. Now, if we notice the right hand side of the last term and the top term, right, the one that we start off equal to 0, right? Notice it is the same term. So in this case, I could say that d t cosine theta, d in bracket t cosine theta, is equal to 0. Okay. Now, if we look at this, what does it mean then, t cosine theta? If you look at that picture, right, the free body diagram, again, the t cosine theta is the component on the x direction, on the vertical line, right? This is your t, then you take component here, right? Become the t cosine is here, t sine is here, right? So t cosine become horizontal line, okay? That d is a small change. So the whole wording of that one is the change in component in x direction, okay? The change in horizontal component of the tension, then of course is equal to 0, okay? So if the change is 0, what does it mean? It means there is no change, right? It means it's always the same, meaning the horizontal component of the tension is a constant throughout the whole cable. Okay, so that is what that equation means, and we will mark that, well, in the book. Therefore, basically, so we know that t cosine theta must be a constant, so we assign name for it. Okay, it depending on the books, on the textbooks. Some call it tx, some call it th, some call it t naught. Okay, it depends. It's it's just a name, basically to emphasize this constant. When you take t cosine, it always one value for one cable. Okay. Well, this is the same thing that I talk about when we talk about the cable with a point load. I said, notice that the tension, when you take the tension into x component, it always the same value. Okay, this is the same case. Well, just so that we can move forward without so many symbols. In this case, for this lecture, we are going to start with T0, T0, or T origin. Okay, and then we'll set this as a equation 1. Now, let's move on. We just do sigma fx. So next, then, well, I just summarize equation 1 there below the free body diagram. Get rid of the proof for now. Then we go to sigma fy equals 0. Okay. Well, that one is good. We know that the horizontal component is a constant, but it doesn't actually let us calculate it yet. So we move on to find the expression. Now, if we do sigma fy equals 0, of course, we take all the components of t into y direction. Then the first one there is the first term t. Take the component is sine theta pointing down, then minus. W is down minus w dx, right? Again, it's remain similar to a constant in that case with a small dx. Then the last term t plus dt into sine that angle, the sine of theta plus d theta. Okay, so we have the term. Similar idea. Now we play around with the math again. Okay, this is the geometric calculus again. Sine a plus b. We also have expression for it. Well, this basic calculus equation, don't worry about it. If I ask you in the exam to prove this kind of equation, I will supply that's cosine a plus b, sine a plus b thing. I will supply in the exam paper. So you should just remember the concept and the idea of how to prove it rather than the details of geometric calculus. Okay, but anyway, let's go. So I just expand the last term then from sine theta plus d theta or sine a plus b into the expression there. Now notice the form is again, then we can argue that if d theta is small, and of course it is small, and it's in radian, which we decide what we're going to use to calculate. But once we say this, we have no more choice. It has to be in radian. Okay, so there we are. There and there. So the same expression we discussed before, so I'm not explaining anymore. Substitute into the top equation, it becomes a little bit shorter, but it's not manageable yet. So if it's not manageable, what do we do? Again, we expand it first, regroup, and hopefully it becomes shorter and more manageable. Okay, let's see. So I times t plus dt into the sine theta plus cosine theta d theta. Of course, from 2 terms times 2 terms, we become 4 terms for it. Okay, so a long one. But now we start to see again, we have minus t sine theta, we have plus t sine theta, disappear. The last term is dt, also times d theta. 2 small numbers times each other, again so small that it is not 0, but small enough to be neglected. So we ignore it. There. And then we left out with 3 equations. Sorry, 1 equation with 3 terms. Okay. Now I'm running down to the bottom of the page. Again, I will get rid of the top. Okay, but you should have it in your printout, in your slide printout already, I hope. There we are. So then we can look at the equation on the top there. Again, I'm going to play around with the last 2 terms, but rather than proving it to the end, I will bring up the end first and then prove that they are equal. Okay, work the way around. So similar. So just this one here is d in bracket t sine theta to du times v, right? So we expand it into that one. Then we use chain law for the last bracket, d sine theta, change into cosine theta, d theta. Okay. Now notice that these 2 terms and the last 2 terms of the top equation are the same. AKA, I can replace that 2 terms. Well, not AKA, sorry, that's wrong wording. I mean, in other words, I can replace those 2 terms with d in bracket t sine theta, right? So let's do that there, and then move wx dx onto the other side. Okay. There. Now, if we want t sine theta, we just integrate both sides. Then we have t sine theta on one side and integration in that term there. Now, notice that this equation have t sine theta. That equation 1, has t cosine theta. Well, we don't really want theta, we want t. Well, we want theta as well, but to solve everything in one go is a little bit awkward. So in this case, by the look of it, right, maybe we could solve it through tan theta, right? Equation 1 divided by equation 2. Okay, that would, there we are. Oh, 2 divided by 1. Okay, then we have on left hand side t sine minus divided by t cosine. T disappear, sine over cosine become tangent, and of course t naught divided by divide the integration term. Okay. But if we look at the triangle, right, we have the x in the free body, we have the x dy. There we are. Right? So this is the usual term. The x dy and then theta is there. What does it mean? It just means that tan theta is dy over dx. So we can substitute dy over dx by in place of tan theta, which then allow us to calculate y. Okay. I will move that last expression on top there. Now, if I integrate again, then we should have y. Well, we will have y. Okay, so that is the general term of expression. Okay, that expression apparently represent the relationship between x and y coordinate of every single point on the cable. Okay, because that x and y is measured on the point of the cable. Okay, now, if we know the geometry, then we can cut free body diagram at any point, and of course we should be able to knowing the angle, because if we know xy coordinate, then we can differentiate for the theta, right? And then we can calculate every single point on that cable. Okay. Now, just for example, to simplify the calculation so that we see the picture clearer. Okay, we will focus now on the case where W is a constant. Basically, it is the uniformly distributed load. Okay, so in a specific case, so that we can see a picture a bit clearer and can start with calculation, make it simplify for this step of our learning. Okay, so if it uniformly, what happens is that W inside the bracket is not Wx. Okay, inside the integration, double integration is not Wx, because then W is just a constant, it's just one value, it's just W, it's not a function of x. Okay, so there we are. That W inside the double integration become constant, which means we can integrate quite simply, right? If it's a constant, integrate the first time, then we have the become Wx plus a constant. This is open integration, right? So when we have open integration, then it doesn't only add x or x squared into the change it into the equation. It's also have to have the integral constant as well. So in this case, because we don't integrate it again, we know that there will be another constant. So in this case, we call it C1 for now. Integrate it again, then we have that term C1 and C2. Okay, so this is actually the equation, the function that describe, as I said, relationship between x and y, basically the coordinate on the cable, the main cable. Okay. Now, look at that. Okay. So basically, this is why it is the xy, because you see when we set up xy axis at the origin, the lowest point in the cable. Okay. If you move according to the cable, right, your xy change, okay, creating that formulation relationship. It is not a straight line, it is parabola. Okay, sometimes it is called parabola cable. Okay, for that reason. So now, however, we keep continue, and this is where the important point of setting the origin at the lowest point become. The first one is anywhere when you set up the origin, the first concept when you put it there, it means exactly x equal to 0, y equal to 0. That creates the first condition. Okay, but we have two constants, if you notice, C1 and C2, meaning we need two conditions to find out both C1 and C2. Okay, the slope on the cable at the moment, we don't know the slope at all, but we know one thing for sure: it doesn't matter what kind of slope it is, what kind of the function it is, at the lowest point and at the highest point, one feature remains if it's a continuous function, which we just proved is continuous function. At the lowest point, the slope is always 0. At the highest point is also always 0. We discussed this before, so let's not put into detail. Okay, but that is something that we have been talking about since the first half of this course. We talk about when we draw the graph of the bending moment diagram and shear force diagram. Okay, so this is something that's gonna happen. So that is why we set it there, because we have two conditions. One, xy coordinate is x0, y0, and then x slope coordinate is x0, y0, slope 0. Okay, that is the case. So if that is the normal integration, then of course the slope dy over dx, we can integrate it. Okay, there. That is the slope function. So the first, this is just argue, what I just argue. Okay, the origin xy 0, and of course because it's the lowest point, the slope is also 0. Therefore, at point O, x0, y0, it gives us with the left hand side equation, it gives C2 equal to 0. On the right hand side, then it slope 0, x0, it also gives us C1 equal to 0. So for the distributed load, for the uniformly distributed load and the origin set at the lowest point of the cable, of the main cable, okay, we can obtain this expression. Okay. Again, this expression to start off with, let's be sure what we're talking about. W is the distributed load that take onto the road, okay, onto the pavement, to the beam, and then hang up to the main cable. That W. In this case, we assume uniform. If it's not uniform, that integration will have to be, you have to have expression for W first before you integrate it, basically. T0, it is the horizontal component, the T cosine, remember? is a horizontal component of the tension. Now, the reason I call it T naught, or in fact T origin, is in fact it happened exactly at the origin. Because at the origin slope is 0, the tangent line will be horizontal line, meaning tangent at that point O is horizontal, which means it's equal to that constant Tx, Th, or whatever you want to call it. In this case, we call it T naught. Okay? And xy is just the coordinate of the main cable, the point on the main cable. Okay? So that is the main equation we have. Well, let's see how we actually apply to solve it, shall we? Okay. Let's say we have this is a cable. Okay. Dimension given, the load given. Okay. So what we want to know is number one, the tension in the cable at point B. You see point B there. Okay. Point B, it is defined that it's 3 meters from point A. Okay. It's indicated down there. And then number two, we want to know the height H from the lowest point of the cable to point B, okay, and the slope at point B, okay. And the last one is what we want to know is the maximum tension in the cable. It doesn't even tell us where it is. It's not T naught. T naught is constant, but it might not be the maximum. In fact, it usually isn't the maximum. Okay. The thing we have now, two problems mainly. Okay. We know that the origin that we set xy is at the lowest point, but apparently because support at point A and point C are different level, okay, it is almost guaranteed if the load is uniform that lowest point is not at the middle of the beam, if not the middle of the span. So it's one of the tasks that we have to do here. One, we don't know what T naught is. Okay. Two, we don't know where the origin is, the origin of xy is. Okay. So let's look at that. Okay. So that is the equation. Okay. We don't know T naught. We don't know xy origin. Where is it? Right. So to start off with, maybe we find a system where we can start. Okay. Let's just assume some distance. Okay. So if I say that from point A, measure horizontally to the lowest point, I call it L. Right, capital L, length. Then of course, because the whole span is 20, if that part is L, the rest is L minus 20. Okay, so meaning the origin is there when I measure from origin to point A. Okay, then I will have the coordinate x is equal to minus L, because I measure x this way positive, measure backwards there to point A, then L. Okay, and of course y coordinate is measured from lowest point up to point A, which is the whole height. In this case, 6 plus 6, 12. Okay, since I get that, then I substitute into the first equation. Still two unknowns, L and T naught, right? So mark it. Now we have one more condition that we know is at point C. Okay, then if we measure from the lowest point to point C, in x is 20 minus L, and of course is in y is only the 6 meters. Okay, the gap between the two. Substitute into the top again, we have that expression. But now we have two equations. We have two unknowns, L and T naught. Right? We should be able to solve it. Well, you can. Well, I think in this case maybe solving it through L should be easier. Well, not much different, but let's go through L. There. So I use equation 2 divided by equation 1, eliminate T naught. Right? T naught is not 0. Okay. So we have that expression. Well, we run out of space. Let's leave it up to the top there. Play around with the mathematics. Move it there. Once we got into that form, we have expression on how to solve that kind of quadratic equation, right? So we have that one. Okay. Minus b plus minus square root of b squared minus 4ac divided by 2a, right? I think something on that line. Then using calculator, of course. This kind of equation tend to give you, this kind of solution tend to give you two answers. It's our duty to know which one is applicable. The later one, 68, well, the span is only 20, right? So it's impossible that the L, that one should be smaller because it's inside the span, will be 60, which is bigger. Therefore, the right answer here, the one that is applicable to this one here, is the first one, 11.72 meters, of course. Okay, now which means that now we know exactly where the lowest point is. Okay, so let's go to question number 1 then. Oh, hang on, let's find T0, sorry. We have two unknowns, my apology. Okay, therefore just substitute back into one of the equations. Of course, in this case I choose equation 1, then find out what T0 is. Once we get that there, okay. Now, let's talk about question 1. Question 1 asks for TB, correct? Now, notice the T0, because we cut at the lowest point, the tangent line is horizontal. Okay, therefore that T, there is no sine, cosine, it's just horizontal. So must be constant that we call T0 in the first place. Then of course where we cut at B, then we have the tension at point B, which is the one that we want to find. And of course the distributed load, the 10 kilonewton per meter. Now notice the span, because we know that from A to B is 3 meters, the question gives us, okay? Then we know that from A to the lowest point is 11.72. Okay, so the gap between the lowest point, point O, to point B, then must be 8.72. Okay, once we have that, then we notice that T0 we already found as well. I think I mark it. Yeah, we already found 57.23, right? Then we know how to calculate that distributed load. It's a normal distributed, it's the uniformly distributed load, rectangle, the area, then the magnitude times the base, right? The W is vertical, the T0 is horizontal, and TB has to eliminate them all. So basically, TB must be equal to T0 plus W times the span, right? Well, when I use these words, plus, I don't mean plus in terms of just scalar, I mean in terms of vector, because it's in different direction. Therefore, we use the sum square there, okay? So that combination, then TB square is equal to T0 square plus W times the span over all square. Then of course put a square root, then we can find out TB. So that's done for TB. Okay. Question number 2 asks, what is the height h? That one. Emphasize the fact that the xy in this equation is in fact the coordinate of the point on the cable. So point B, then we know x because we already measure 8.72, right? From origin to B, but it's minus, it's backwards, okay? So we substitute into it, there. We also know T0, okay? There. That, the left-hand side is expression for the xy, the right-hand side is expression for the slope, okay? I just substitute only T0. Now, to get at B, then I have to substitute x equal to minus 8.72, right? Because we measure to the left-hand side. Substitute into that left expression, it doesn't matter because it's square anyway. But then we work out y is equal to 6.643 meters. Okay, so we can work out the coordinate of point B. Basically, we know x, we know y. Then, of course, we can actually substitute x into the slope equation. Then we get the slope as well. That slope is in radian. Okay, okay. So question number 2 is done. Okay, last one then. They ask for the maximum value. Okay, so let's look at general free body diagram first. Okay, let's say we cut somewhere, and if we call it just Lx, any Lx. Okay, how do we calculate that T, that tension at any point? We have T0 57.23, right? That one is T0, meaning the cut on the right hand side is at point O, on the left hand side is anywhere so far. So we use just symbol Lx for whatever the length we cut. So if we put with the same idea, okay, T has to be equal to the combination of T0 and the sum of the W. So we can put in that equation. Once we put in that equation, notice that the only thing that can vary in that equation is Lx, right? And if Lx increase, T also increase. Okay? This is not x, this is just the length, okay? If Lx reduce, then it become T become smaller. Okay, so basically we should go for the place where you have the maximum span. Okay, in that case, the maximum span from the lowest point origin to point C is only 8.28. But the maximum on the left hand side, again, this is not coordinate x, this is just the length, the span. Therefore, it is 11.72, which is bigger, of course. So basically, in this case, the maximum tension will happen at point A with the span here. T is maximum when the span is longest. Therefore, the longest span is from origin to point A. Therefore, it's 11.72. Substitute into the equation. There we go. Then we have Tmax, or the maximum tension in this cable at point A. Okay. There we are. The three equations, the three answers. No, sorry. Question 2 comprised of 2 questions. Sorry. So 4 questions, 3 group, but 4 questions. Then therefore 4 answers. And that's it. Okay then, that's the end of the lecture for today. Thank you very much for your attention, and I will see you in class very soon. Thank you very much. Bye-bye.